I'm David Peto, the CEO and co-founder, as I said, Andrew Rogers, CTO and co-founder of General System. The world is dynamic. Outside of this room, billions of people and tens of billions of things and machines are interacting, reacting, making decisions every single second. It's how the world works. It's constantly evolving, constantly developing. It never sits still. It never stops. We need to harness the data that comes off of all of these people and machines and things if we're going to solve many of the hard problems that we see in front of us. Everything from climate change to remote sensing work, to imaging the Earth to understand better how our supply chains work, security, you name it, all rely on this. The problem is the world is real-time. It runs at the speed of reality. But the challenge is that our data processing and the way we work with this data runs 24, 48 hours behind. Now, why is this? This is because of the post-processing and the work we have to do to get to work with these kinds of data. It's not about landing just the real time, that's fine, but you need to be able to interrogate your real-time data against your stored historic data together to get context. Because with context, you get the why, not the when. You want the how. And you need to be able to do that when your incoming feeds can be millions of events a second, potentially, or higher. And you may have hundreds of billions or more of stored records that you need to be able to interrogate together to achieve that answer. And there are limitations in our data processing today that make that a huge challenge. So what is General System? General System is a new kind of data infrastructure platform, like Databricks is a data infrastructure platform. We're a data infrastructure platform, but one that's been specifically created to handle enormous quantities of spatiotemporal data, space and time. Those two data models pathologically hate each other. So to be able to bring them together into a single index method, we'll come on to that, is a genuine breakthrough we're really excited to walk you through today. And at the heart of it is a new form of data processing engine stack that bears no relation to anything else. There's no open source, we're not using anybody else's system. The whole stack, top to bottom, is new. And those combined breakthroughs bring a new level of speed, a new level of scale, but also a new level of cost. Because one of the challenges with all this data is that the cost of processing it is outpacing the revenue and the value it creates. So unless we fix that, there's no point in doing it. So why are we facing this challenge? It's this. It's the cars out there that are roving sensing platforms. It's the phones we carry in our pockets. It's the satellites we're throwing up into space to image the Earth. It's the sensors we're putting out to follow pollution, the things we're putting in our homes, and in the future, robotics, drones, spatial computing, augmented reality, you name it. This is only going to get worse and worse. But as I said, it's really, really hard to work with this data. So Andrew, why is that?
Right, so there's a few things to consider when working with spatial temporal data, and some of these challenges are actually relatively unique to the data type. So the first is that, as many of you will be familiar with, is that ingesting, indexing, storing, analyzing this data is extremely slow and actually very high latency, even more so than it is for many other data types. And there isn't a single root cause for this. There's actually many. The interesting thing, though, is that this isn't just a challenge for people who are doing real-time use cases where time to insight is really critical. This actually, the inability to work with this data quickly and efficiently is also a major cost driver when doing even the offline batch analysis type workloads. The other interesting consideration is that the records that you typically have in spatial temporal, they're actually quite small. They're relatively small, but you have many billions of these records. And this has really interesting implications for the way you process and handle this data. So the typical spatial temporal analysis workflow is essentially iterating over found relationships across entities and places and time. And when you do these types of iterative inspection of these types of relationships, essentially means you need to be able to do fast ad hoc queries across these relationships, which means indexing and data locality across all of these attributes. And the part about the records being small that makes this difficult is that when your records are small and you have a lot of those records, your indexes will actually be larger than the underlying data in many cases. And so what happens is that we build these lovely indexes on the spatial temporal data, and even though the data itself may be a few terabytes, the indexes can actually be even larger, and that means it doesn't fit in memory. And lastly is that one of the techniques that we often use in other kinds of data analytics is to do data reduction by sampling. This doesn't work very well for spatial temporal data for many use cases. And the reason for this is that the value of any individual record is highly variable and context dependent. And as a simple real world use case of this, consider the measuring or detecting changes in the road networks based on sensor observations from automotive. And this is actually a real world use case, it's very common. So for a busy highway segment, you may see 1,000 records a day. Any additional records beyond that are actually quite low value. You'll have other road segments where you might see 2 records a month. And so those ones are much more highly valued. And people are like, well, we can discard the low value ones and keep the high value ones. The only way to know if a record is low value or high value is to query the context of what you've previously seen, which is actually more expensive than just storing the thing.
Perfect. Thanks, mate. Right. So now that we've laid out how damn hard this is, let's show a use case where we use GS to solve some of these problems. So this is a case study with a real customer. Names and locations have been changed to protect the innocent, so please don't try and find a Beans coffee store next time you go to Sydney. The name is different, the locations of the stores are different, but it is a real use case. So, Beans Coffee have 18 locations in Sydney. They have them primarily around the metro stops to maximise football, and on as well they have about 4,500 customers, 4,520, who use a Beans app to get promotions and various other stuff, and they're happy to share their location of movement as they go through. And in June 2022, Beans had a big drop-off in revenue, and they were trying to look at ways to boost their revenue, how to do that. And they realized, obviously, their stores were in certain locations, and they wanted to experiment with using coffee bikes to get the coffee to the customers rather than trying to get the customers to the store. And so working with GS, we help them solve some of those problems. So we're going to show you 3 things. We're going to show you an analysis of static mobility data at very, very large scale. I'll come on to that, to understand the pattern of movement in the city across a day on an hourly basis. We're then going to run some customers' pattern of life, and we're going to show how that fits into the picture, and then we're going to run a live demo, yep, here we go, on stage, of running live queries on these enormous data sets to show just how powerful this is, and also how light it is on its compute. So first one is the analysis of the very, very large scale mobility data. So cast your minds back. It's the 1st of June on Thursday on June at 8 a.m. Okay, so here we are in Sydney. So this is the data of all the movement around the city. Obviously you can see here, if you can see my pointer, but you can see obviously the roads are really busy here as everyone is coming in. Here are our coffee store locations at the metro locations. They've got some which are slightly further out. That's Westfield Shopping Centre there. And there's the business district, which is starting to busy up. Note, the university, which is here, mysteriously not busy at 8 a.m. Wonder why. Right, here we go, 9 a.m. All right, so the roads have started to die down now. That's fine, that's not a surprising thing. The business district here is really starting to busy up. Now, interestingly, they've only got 1 coffee store in the business district. But look at the amount of footfall they've got there, right? It looks really light in terms of the store count to the level of footfall that's coming on there. We'll come back to that. Okay, 10 a.m. Things are starting to die down there, but we're starting to see some of the infrastructure and the ports get busy up here. Also, interesting when you can work with the scale of data as fast as we were doing here, there's actually a drop-off in the data at 10 a.m. There's a glitch in the data set, which is really easy to see here now that we can actually visualize this. But it's key to say that these hourly reports that were being run were taking under 2 minutes. And the underlying data set, I'll get to the scale of the data set we're interrogating to do this. 11 a.m. shopping starts to get busy over here at the Westfield Shopping Centre, for example, so we can see the movement of the people around there. 12 a.m. everyone's coming out for their lunch. Again, look at all this traffic and footfall we're missing out here because we've only got 1 store, even while other areas are much quieter. Look out here, right, there's really nobody here at this particular point in time. Let's play this through, 1 o'clock, 2 o'clock, 3 o'clock. Now this is where it gets interesting. Beans' revenue starts to drop off at 3 o'clock normally. Don't have a lot of people coming into their stores, but look how busy it is here at the business district, right? Everybody, it's packed. And same around the shopping area and various others. So why are they not getting the footfall, and how can they get to the back of this, and how can they deal with it? Just playing on through, 5 o'clock, people are starting to go home, but you can see, funnily enough, being Australia, the beach, starting to look busy, okay? Everyone's heading down there. All right, and we're at the end of the day here now, right? So what we can see is that dynamic movement across the city really, really simply. We can look at the store locations. They then gradually went down to a street level of the analysis to get the understanding of the movement, and literally down to a street level to try and get an understanding, which we'll show you. But they then decided, okay, we think we've got enough data, or getting close data, to come up with a coffee bike schedule. So this is the schedule of the coffee bikes with all their names. We're going to go look at Davina a little later on and do that. And the locations they felt were the most likely ones to be able to generate revenue by delivering that. They then did a second analysis, which is of the pattern of life of some of their first-party data, so 20% of it, taking a random chunk. The understanding, did that match to the actual use case and movements of their customers? So interestingly, quite a lot of them are students, which don't go anywhere near those areas, so they spend more time out towards the shopping environments and the beaches in this example. But quite a lot of people, it confirms, are all in that business district, even if they're customers where they've only got one location, right? Which is a real missed opportunity to be able to deliver that shot of caffeine to people so they can keep on with their very busy day. Okay, so we've run those historic analyses. Now we're going to show the dynamic part of this. So I'm going to switch to this. Okay, so this is the underlying data set that was used. This is 85 billion records of mobility data that we're looking at here. It's about a 3-month period of a very, very wide area. We're zoomed in on Sydney here, but we're going to go run some queries on this right now while we're running. So here we go. Okay, here we are. Right, so we're running through. So what we are doing here is we are, in fact, running a query every second against this entire 85 billion record data set. And we are extracting 5 minutes of data, sped it up to make the point, because you don't want to sit here and watch this for hours. But actually, that's more data. We're querying it harder and faster. And we are taking that data and we are aggregating it in real time, and we are delivering it into hexes, so H3 hexes. Although, if you come and talk to us afterwards, we don't need to use H3 for various reasons. And this is a very large multi-vertice polygon that we're doing the point and polygon queries inside. So this is not a bounding box. We can handle thousands of vertices while we are querying this. But you can see here as an example, these orange tracks, these are simulating the movement of the bikes. And you can see here, for example, that Davina has stopped up here, right? So not going anywhere. But over here to the left, I'm colorblind basically, but there's a part, I think, there, right, which is looking really, really busy. So we could now dynamically ask the driver or the rider of Davina to move the bike over there. Okay? So that's 85 billion records. It's being queried every single second for 5 minutes worth of data, and it's happening every single second as we're going through. The really exciting thing about this is you might be thinking this is running on some massive cluster, right? We're burning down AWS East Coast region in order to produce this. This is running on a fractional VM on a single CPU-only server. No GPUs, the data's not in memory, this data is on a disk. And we're running these level of queries and speed on that level of data set, which is just so exciting to start to be able to show you guys. And you really are some of the very first people in the world to be able to actually see this running. So, why is it so hard? What are the problems we're solving here, Andrew?
Right, so you could kind of call this slide lessons I learned the hard way. And this really gets into what are we doing differently that allows us to run these workloads on machines that seem a lot smaller than they should be to actually do these workloads. So, one of the things we do in any kind of scalability is sharding. Everybody knows about sharding. Data models, we shard them based on assumptions about the distribution of both the data and the workload. Spatial temporal is notoriously unpredictable in terms of how the data is actually distributed and how queries are distributed over it. And so you get hotspots and scalability issues like that. For this particular instance, we're actually using, we don't actually do static sharding. We're actually doing dynamic sharding. This data was loaded using a single shard that then adaptively resharded based on the actual pattern seen in the data in real time, adaptively and dynamically as the data was actually in the system and being used. And just to be clear, this actually has probably about 1 million shards underneath the hood on that one EC2 instance. And just as an aside, storage engines usually don't like it when you create and destroy shards that quickly. One of the other things that we've done here is that much of the latency that you see when we talk about how slow and high latency the pipelines are for dealing with this data, a large portion of that latency is actually due to just data motion, moving between system to this system to this system. All of this workload, all of the indexing, the storage, the query processing, It's running in a single process. That means that when data shows up from a live stream, it's reflected in operational queries within milliseconds. All of that latency, it's gone. One of the other really important points, and I mentioned this, I raised this earlier, is the indexing and storage costs. And a lot of the storage costs actually are around indexing. The raw data, for like this data set, it's not that bad. But the indexes are actually quite bloated, and the fact that they actually have to sit on disk means the queries would be slow. So for the storage data, the indexing here actually uses a very novel type of high dimensionality succinct index. And for people who are like computer science nerds, succinct indexing is like a very compressed type of index. So the actual index here for this data set, it not only does it fit in memory, it probably could fit in the CPU cache. Can't guarantee that, but it's going to be about that size. And lastly, and this was something that will be very familiar to everyone here, is really how do you make the data interoperable? So spatial temporal data sources frequently are global in extent and nature. So when we're actually doing these operations, as David said, we're doing like polygon searches, proper polygons. These are actually being represented on a sphere. We can index objects out past low Earth orbit. It's an actual 3-space model of the planet. And this allows us to bring in many different diverse data sources that may have not been designed to interoperate, but we can actually register it to a model of the world that looks exactly like how we kind of reasoned about it personally.
Oh, my buttons. Oh, there it is. Hang on. Sorry. Failure. There we go.
Yeah, so where do we see the future of spatial technology going? The direction where it's heading is the use of multi-attribute online indexing. That's kind of like the class of problem that we do, and that keeps your indexes small. It also means that you can do real-time indexing. And this has actually been the gap, is how quickly can you build the indexes so you can do all these clever searches across the relationships. Fast and efficient querying of spatial temporal relationships between entities. So that's actually pretty self-explanatory. The ability to do this quickly, not using batch processes, not waiting a long time to get the answers, be able to do it interactively as data scientists to actually run your query, immediately get feedback, and then do another query that's based on the output that you got from the query you just ran. Real-time contextual alerts and fast querying of batch data. We're not just watching this data go by. When events come in, we want to say, oh, there's an anomaly here in this part of the city. Take that event and say, why? What are the causal factors that we can see across all of this data that's streaming in that might indicate why we're seeing this event in this particular location? And lastly, the ability to run these on a single server or on a small cluster inside the cloud. One of the really big problems people who are working in this space, and it's been a problem for a long time, is the cost of working with this data. People who are already working with this data, frequently you'll see the cost rising even faster than the data that they actually have to deal with. And this is a huge problem for finding value.
Perfect. Thanks, mate. So some other use cases. You've seen one there, but we see these obviously everywhere, right? So we've got last mile delivery. It's not actually, funnily enough, a last mile problem. When we talk to customers, it's a last 100 foot or 100 meter problem. Did the driver actually make the delivery? Did the driver randomly hit the button in advance hoping for another job faster? Did they remember to press the button in the first place? Right? It's actually where you need to bring state in. You need to understand history to understand, is that normal, what is happening there, as an example. So get an extra delivery in an hour as a logistics company. That makes a huge difference. Being able to, for example, know those drivers are passing by a store and sending you a message going, do you want a bottle of wine with that? How do you increase the revenue for that? The behavior analysis of fleets for delivery, trucking, shipping, all those other areas. We've had some amazing conversations here about port congestion, how you can speed up the movement through there, telcos, those masts that you all see up, the 5G RAN nodes that sit on there. They're not omnidirectional. They don't put a universal pattern out of connection for your phone. So actually, some of them sit on motors. So if you could understand the real-time movement of your customers and the patterns of history, pattern of history where they normally are, you could actually move them on motors. And on and on and on and on. We see this everywhere. The key thing, however, to say is you do not have to have millions of events a second and hundreds of billions of records to get the benefit of general system. It's amazing, even if we're only dealing with 500 events a second, how that builds up into billions of stored records really quickly if you want to do analysis on that data and bring that context into play. And the other thing is that this is incredibly simple to use. This sounds very complex, but it's not. So this system runs on AWS. You can come to our website. You can sign up. There is an API key. You get the API key, and we have sandboxes with hundreds of billions of records, 92 billion being the main one, with synthetic data that you can start to query immediately. If you use Jupyter Notebooks, if you use Python, if you use Java, whatever else, you can come in and use it off the back of it and get access to the power of the system and start to make the most of it. And we are hugely excited to bring this out. We're actually 6 years old, but we've been working very quietly in stealth, building and developing this, and we're now coming up publicly. So to do it here at Spatial Data Science is a real privilege. Thank you so much for listening. Hope you found it interesting. Hopefully it gets your mind racing about what you might be able to do now, because frankly, we see data science as the driver of change.